Hello everybody, today we're going to be doing this Fall 18 midterm question. Now this is another Lenz's law / Faraday's law question. Now I particularly like this question because we have two elements that are changing with respect to time, our magnetic field as well as the radius of our ring, and we're asked to find the direction and the magnitude of the induced current. Now one thing that's important to consider when we see questions like this is which component will become dominant later under small t conditions. And we'll see how this plays out later in the question. However, that is something that you should consider when you see a problem like this. Now, let's look at our magnetic field. And we see that our magnetic field is pointing in the positive x direction. However, we're on the zy plane. So it's not immediately obvious whether positive x will be into the page or out of the page. Now, there are several ways to figure this out, such as the right-hand rule. However, what I like to do is to draw our standard planes. First in 2D, where x and y is like this, where positive x is to the right, positive y is up, and positive z is out of the page. And our standard 3D plane is of course like this, where positive z is up, positive y is into the page, and positive x is to the right. Now, I'd like you to imagine you are transposing this plane onto our figure. And you can pause the video and try to imagine this yourself, but if you do, you'll see that positive x is in fact out of the page. Now, we can inspect the equations that we are familiar with, and in order to calculate our induced current, we first have to calculate the magnetic flux through our loop. Now we can see that magnetic flux is equal to the integral of B dot dA. This is because vector flux is defined as the dot product of the vector onto the area. Next, we can look at this equation. Now this equation is a combination of Faraday's law and Lenz's law. Faraday's law describes the magnitude of our induced potential, our induced electromotive force. And this is by taking the derivative of the change in flux with respect to time. N represents the number of loops in our ring, or our square, whatever it is, but in our case, our ring only has one loop, and therefore n will be 1. And this negative sign represents Lenz's law. And Lenz's law says that we're always going to want to induce a potential to negate that change in flux. We don't like the change in flux, and we want to go back to how we were before, and that's what its negative represents, and Lenz's law represents. Finally, our I induced will be the induced electromotive force, or VEMF, divided by the entire resistance of the loop. Okay, now let's look at the magnetic flux through our loop. Now, when we're looking at our elements, our B and our R, we see that neither is changing with respect to area, but rather with respect to time. And so, our integral can be simplified to the dot product of B and A. And the dot product of B and A is B times A times the cosine of the angle between them. However, we see that B is pointing out of the page in the positive x, and we see that A, the area vector, is also pointing out of the page. So they are parallel lines, and therefore the angle between them is 0. So we can further simplify this to B times A times cosine of 0, which just equals B times A, of course, because cosine of 0 is 1. Now let's rewrite what B is and what A is. So B is equal to x hat B naught cosine omega t, and A is equal to pi r squared, where R is equal to r naught plus alpha t. Okay, now let's rewrite what our flux through our loop is, which is just going to be B. So B naught cosine omega t times our A, which is pi r squared. Excellent. And now let's look at Faraday's law. Now, as we mentioned before, n is going to be 1, and our change in flux with respect to time will require us to take the derivative of this function with respect to time. And so this function looks a little bit complex at first, so we need to break the derivative down. And to do this, we're going to use the product rule. And what does the product rule say? The product rule says that the derivative of some function of x times another function of x is equal to the derivative of the first function times the second function plus the first function times the derivative of the second function. So let's rewrite this in terms of our induced EMF, of our VEMF, and we'll come to VEMF equals negative d flux dt, of course, because n is 1, which equals negative of b times dA dt plus a times dB dt. Excellent. And now we can do our derivatives because we have broken them down into components, and they are very easy to do as components. So let's begin by taking dA dt, and dA dt is going to be the derivative of pi r squared, and we're going to have to utilize the chain rule because r is a function of t. So we have a function within a function, which of course means we have 2 pi r times the derivative of the inner function, which is dr dt. What does dr dt equal? Dr dt simply equals alpha. Now, what is dB dt? We again have to utilize the chain rule because we have our outer function of cosine and our inner function of omega t. And so dB dt is going to equal the derivative of the outer function, which is the derivative of cosine is negative sine. So negative b naught. Let me move this a bit further to the left. Negative b naught times sine omega t times the derivative of the inner function, which is just omega. Now that we have this, let's write our total induced VEMF, our total induced potential, which just equals negative. Right, we're keeping that negative on the outside, which represents Lenz's law, but we'll deal with it later. Negative b times dA dt, so b naught cosine omega t times 2 pi r times alpha, of course, plus a, which is pi r squared, times dB dt. And we said dB dt is negative b naught sine omega t. So this becomes a negative. And this is b naught sine omega t times omega. And we can pull out some constants. So finally, we get that our VEMF is equal to negative b naught pi r times cosine omega t, and we took out a pi and we took out a r, so 2 alpha, minus, and we took out a pi and we took out a r, so only 1 r left here. We took out the b naught, so sine omega t times omega. So finally, this is our induced potential, our VEMF. So now we can calculate our induced current. Now, our induced current says we need to divide our VEMF by the total resistance of the loop. Now the loop, how do we calculate this? We calculate this by multiplying the resistivity of the wire times the entire length of our loop. And of course, the length of a circle, the circumference of a circle, is 2 pi r. So our R resistance, of course, so we don't confuse it with our R of our ring, is rho times 2 pi r. And rho, of course, is our resistivity. And now we can write our I induced is equal to negative B naught pi r over rho times 2 pi r times cosine omega t times 2 alpha minus, let me move this, minus r sine omega t times omega. And now we need to go back and we need to think which component is dominant under small t conditions, either dA dt or dB dt. And of course, we're looking at the derivative. That's what we care about. And so we see that under small t conditions, i.e. when t is 0, our dB dt is 0, because sine of 0 is 0. Whereas our dA dt, our element associated with dA dt, cosine of 0 is 1. So obviously this component is the dominant one under small t conditions. And this component, as we see from earlier, is dA dt. Now we need to consider what is happening at dA dt. We see that the radius of our ring as time increases. And if the radius of our ring increases, the area of that the ring encloses also increases. And if the area is increasing, that means that the flux through our loop is also increasing. So what does Lenz's law say about it? Lenz's law says we don't like that change. We will produce a potential to fight that change. Now, where does the B field, the change in B field, want to induce the current to? We know that a changing B field, increase of the current around the changing B field will go in the clockwise direction. So, for example, if you had a constant B field and a constant flux, no current would be induced. However, if the flux is increasing, then it's going to want to induce a current in the clockwise direction around the increase in flux, which of course is the direction of our B field. And so if our B field is pointing out of the page in the positive x direction, and the flux through our loop increases, then the change in flux is going to want to create a current in the counterclockwise. However, remember, Lenz's law says we don't like that change. We want to fight that change. We don't want that increase in flux, and we want to come back to how we were seconds ago before the change in flux occurred. And so the I induced will be in the clockwise direction. Now, of course, this negative here refers to the negative from the counterclockwise direction. And so, finally, we can write that our I induced is equal to B naught, and we can cancel out the pi and the r, times 2 rho times cosine omega t times 2 alpha minus r sine omega t times omega in the clockwise direction. So while this problem seems a little daunting at first, we see that once we break it down and we understand every element, it's actually not very difficult. Now, there are some takeaways I want you to take from this question. The first one being able to see these directions. It's very critical to understand which direction is positive and which direction points where. And being able to discern these directions is the make or break between fully understanding a question and not understanding a question at all. So that's the first takeaway. The second takeaway is what does Lenz's law and Faraday's law says. Faraday's law gives us the magnitude of the induced EMF, while Lenz's law tells us which direction will it go. And we always want to fight the change in flux. Whether it's an increase in flux, we want to go back to how we were. It's a decrease in flux, we want to go back to how we were. We don't like that change. And that's the second takeaway. Lastly, the last takeaway is being able to recognize which component is which. Now, when we break it down to terms like this, it's easy to see that this element is the ADT and this element is the BDT. However, sometimes it'll be more difficult to discern. So another trick that you could use is you could see that perhaps cosine omega t is very similar to our original B. So it's not dBdt, whereas sine is, of course, is the derivative of cosine. So we can see additionally that this is dBdt. And it's really important to discern this because this will later also make or break you being able to understand which direction the current will be induced. Now, thank you for watching. I hope this was helpful, and good luck and thank you.